Solution concentration is something that is really important when you are working in a lab setting. So this is something that hopefully you covered in depth in your prep classes, but we're going to go back over some of those concentration terms right now and do a few practice calculations just to refresh and make sure we all remember how to use these different concentrations. So here's just some of the different concentrations that you can encounter. The most common one we use in chemistry is obviously going to be molarity right there. So that's where we get our moles of our solute over liters of our solution. Molality we use not nearly as frequently, but it does come up, especially when we talk about things like colligative properties. So we look at things like freezing point depression, boiling point elevation. It's very similar to molarity, but instead of the moles of solute being over liters of solution, it's over kilograms of the solvent. Okay, mass percent, mass of part over mass of the whole, so the mass of the solute over the total mass of the solution times 100. Parts per million and parts per billion are very similar to mass percent, except instead of being multiplied by 100, they're multiplied by 10 to the 6th and 10 to the 9th respectively. We use parts per million and parts per billion a lot of times in environmental considerations. When I'm thinking about contaminants and a water supply, I hopefully have those there in trace amounts. So parts per million and parts per billion is what we use for those sorts of things. If you ever read a water quality report or an air quality report, you'll see things in parts per million or parts per billion more frequently than outside of those contexts. Mass volume and volume percent. As a chemist, I don't know that I've ever actually used those in a practical setting. I have seen them in some lab settings where more biological research is done. So I'm not sure that they're used as much as chemistry. I personally haven't really encountered those so much. And then mole fraction is something that we use when we start looking at some of those other solutions. This cuts off a little bit, but we're looking at the moles of the solute over the total moles involved with the solution, so solute plus solvent. It's a fraction because we're multiplying it by 100. If we multiplied it by 100, then it would be a percent, but it's the moles of the part over the moles of the whole. Usually it's done in terms of solute. Sometimes you can do the mole fraction of the solvent, but you typically see it in terms of the solute. We see this more in settings like with Raoult's law, and when we look at how a solution impacts the properties of the pure solvent, such as we get with the molality as well. So that's where we start to look at those things more frequently. So we're going to look a little bit more at that molarity and mass percent and kind of refresh some of that. Okay, so here I have an example where we've got some acetic acid, has a mass percent, 20% by weight acid. We've got 35 mils of this acetic acid solution. We have a density for the solution, and we want to know in 35 mils of this solution at this density and this percent, how many moles of acetic acid do we have? And this is important because remember, if we're trying to do reactions, we can't compare grams and grams. We have to compare moles to moles because if I have a gram of acetic acid and I have a gram of some other substance, they're going to have a different number of particles. But if I have 1 mole of something and 1 mole of something, because of Avogadro's number, I would have the exact same number of particles. And so we have to compare through moles because that's where we have that reference point to the same number of particles. Okay? And so what we're looking at with this problem is we need to go from milliliters of solution over to moles of our acetic acid. And this HAC, that's a standard abbreviation for acetic acid. The AC is the abbreviation for the acetate anion, and then the H is the ionizable proton that makes it acidic. All right, so there's where we need to go. So point A to point B, moles of solution to moles of acetic acid, or milliliters of solution to moles of acetic acid. We have a few more steps we have to go through. I can't go directly from milliliters of solution to moles of acetic acid. Now I have a few pieces of information here. I know the density, which gives me the grams of solution per milliliter of solution, because that's not the density of just the acetic acid. That's the density of the acetic acid solution. Okay, and so when I have the density here, this is the density of so it's important to remember that's the density of the whole solution. Okay, but I do have another piece of information that will let me extract out information about just the acetic acid, and that's that 20% by weight. Okay, so we can build a bigger roadmap. So I need to go from that milliliters of solution to moles of acetic acid. From my density, I can go between volume of solution to mass of solution. Okay, so we can start with that milliliters of solution and get 2 grams of solution. Okay, now with that percent, I can go from grams of solution to grams of just the acetic acid. And then how do we go from grams to moles? The molar mass. I can go to moles. Okay. All right. To give myself enough space to write, I'm going to go ahead and switch to a blank slide. All right, so let's take that roadmap and fill all those pieces in. So 35 milliliters of solution. I have 1.0269 grams of solution in every 1 milliliter of solution. I have 20 grams of acetic acid for every 100 grams of solution. Okay, and then I have 1 mole of acetic acid and 60.05 grams. Okay, and that 20 grams of acetic acid per 100 grams of solution, that's from that 20% by weight acetic acid. Okay, because remember that we were given that in the problem that we have 20%. Okay, so that's how that put in there. Okay, so now that we have all the pieces, now we can pull out a trusty calculator, punch that all into the calculator, and we come up with 0.1197. Okay, are we done at this point, or is there one more step that we have to take? We do have one more step. We need to round to the correct number of significant figures. So when I look at this, I have 2 sig figs for my volume. I have 2 sig figs for my percent by weight, because if you look back at the problem slide, there was a decimal point at the end of that 20, so you get to keep both of those numbers. And then my density, I have 5 sig figs. My molar mass, I have 4. So how many sig figs do we get to keep? We get to keep 2, because we have to keep the lowest number of sig figs. So we're going to round this, and we are going to end up with 0.12 moles of acetic acid in 35 mils of that particular solution. Okay. All right, let's look at another one. So here I need to prepare a 0.25 molar solution of hydrochloric acid. Commercial hydrochloric acid, if you buy it in its concentrated form, it ships at 12.4 molar. This is pretty crazy stuff. Actually, if you buy concentrated acetic acid for a lab, when it ships, it doesn't ship like with just standard packing materials. It ships like in a whole bunch of stuff, and then the bottle is actually lined on the outside with a kind of plasticky coating. So if something were to happen during shipment and the glass shatters, then the acid still has a chance of staying contained with that plasticky coating that's on the outside of the bottle. This stuff is pretty crazy. And if you recall that hydrochloric acid is actually made from hydrogen chloride gas that is then dissolved into water, because this is the most concentrated you can get it. When you take the lid off of concentrated hydrochloric acid, you get some vapors that fume up. So this stuff is pretty crazy, but that's how we get it commercially. All right, so let's say you got a job as a lab tech. This is a really common thing. I used to do this all the time when I was an undergrad and I worked as a lab tech, is make solutions like this. And so you got a class that's doing this experiment. You need to make 1.5 liters of 0.25 molar hydrochloric acid. So we're going from a more concentrated solution to a less concentrated solution. So can you think of a term that means less concentrated? Dilute. So this is a dilution, okay? And so for dilution, we have a really handy equation. We have this M1V1 equals M2V2, okay? Now, this is an inversely proportional relationship, all right? So in this situation, we're trying to make a less concentrated solution, and we're trying to make a whole 1.5 liters of that. And so when we look at that inverse relationship, when one variable goes up, the other variable is going to go down. And so we would expect that we would not need a whole lot of that concentrated 12.4 molar hydrochloric acid in order to make this particular solution. Now, one thing I like to do when I solve equations like this is I do actually like to go ahead and define my variables, because in this problem, it's not always written in a linear fashion, okay? We start off with our target concentration, or my diluted concentration. And then we're told what the concentrated original solution is. And then we're told our final target volume. So I find it easier to define the variables so that I don't get them all mixed up within the problem. So we're going to have an M1 and a V1. And we're going to have an M2 and a V2. All right. And typically speaking, when we're doing dilution, we take the M1V1 to be the more concentrated solution and the M2V2 to be our target dilute solution. All right. So M1, concentrated. So I have 0.25 molar versus 12.4 molar. Which one's more concentrated? The 12.4. Okay? I want to prepare that 0.25 molar. So that's my target. That's my dilute solution. Okay? I want to know how much of the concentrated acid I need. So that's what I don't know. I don't know V1. I don't know how much of that concentrated acid. And then I need to make 1.5 liters. All right, so there's my variables. And then all that's left is just to rearrange to solve for the variable with a question mark next to it, which happens to be V1. I'm going to go ahead and switch to another slide and give myself more room to write. Okay, so we're going to rearrange. So V1 is going to be equal to M2V2 over M1. Okay? Pretty simple at this point. Now we're just going to plug it all in. We're going to get our 0.25 molar times our 1.50 liter over our 12.4 molar. Okay? When we do this, we get 0.030. Okay? Well, let's figure out what units these are, because this is molarity. Oh, that was interesting. This is molarity and this is molarity. So we're left with liters. Now, in the lab, what are our graduated cylinders usually done in units of? They're done in milliliters, which is why the problem asks for this in milliliters. We're going to get 30 milliliters. Okay? Now, here's a question. Think back to prep chem. How do we make this solution? Well, our target final volume is the 1.5 liters, right? So I don't want 1.5 liters of my solvent, which in this case would be water, and then 30 mils of my acid, because then I'd have a little bit more final volume. So what I need to do is I would take the 1.5 liters, subtract off the 30 mils, and then I'd know how much water to add. Or I would use a volumetric flask where my volume would be the 1.5 liters. In the flask, I would pour in my 30 mils of my acid, and then we would go from there. Usually though, you want to add concentrated acid to water, so you'd probably like I don't know, half fill the flask with some water, and then you'd add the acid in, get it all mixed up, and then finish filling it up with water. Okay. Okay. All right, let's take a look at another problem. Okay, so now I have a 35% solution of glucose. We've got a density of the solution. So remember that density is grams of solution over volume of solution, not the glucose by itself. We want to know the molarity of the glucose solution. Okay, so remember molarity is moles over liters, and we're looking at moles of glucose over liters of solution. Okay, so that's what we're looking for. So what pieces of information do we have here? Well, we have a mass percent. Okay, mass percent is going to give me grams of glucose over grams of solution. We have a density, which is grams of solution and volume of solution. Oh, let's think about that for a second. Can we use those two pieces of information to help build this? Well, absolutely, because if I know grams of glucose, I can use a molar mass to get moles, right? And if I know grams of solution and I have a density, I can get a volume. So this is going to be an interesting one because we have to convert two different units. All right, so we're going to take our grams of glucose over our grams of solution. All right, and we're going to get this from the mass percent. Okay, that's coming from the mass percent there. So we have to do two simultaneous conversions. So from the top, I'm going to go from grams to moles. That's easy. And we're done with the top because we need moles of glucose on the top. On the bottom, okay, we're going to need to go from grams of solution to milliliters of solution. And then from milliliters of solution to liters of solution. Okay? All right, let's try it. Okay, so I have 35 grams of glucose in every 100 grams of solution. Okay, we said for that top we need to go to grams to moles, so I'll use the molar mass. 1 mole of glucose in every 180.1 grams of glucose. All right, there's our top. We're done. Now we got to convert the bottom. So we got to make sure that we are canceling out the grams. So in this, and we're left with volume on the bottom. So in this case, we're going to put that 1.28 grams of solution over 1 milliliter of solution on the bottom. And then we're going to take 1,000 mils over 1 liter. Okay, we can check. Let's cancel out grams of solution. Let's cancel out grams of glucose. Let's cancel out milliliters. Am I left with moles over liters? I am. So it looks like we did it okay. All right, again, grab your calculator. Okay, we're going to end up with 2.487. Do a sig fig check. You should get 3. So you're going to end up with a 2.49 molar solution of glucose. All right. Okay. One more example. Let's look at some stoichiometry. All right, we've got an acid spill in the lab. We're going to clean that up with our sodium bicarbonate. Here we have an equation for a neutralization of sulfuric acid. Now, okay, I'll be honest here. If we have an acid spill in the lab, I'm probably not going to stand there and go, well, how many milliliters of acid did we spill? And then run this calculation. Usually what we do is we just dump the sodium bicarbonate on top of the spill in excess until it stops fizzing. But if we want to be frugal and make sure we only use exactly the amount of sodium bicarbonate that's going to neutralize our spill, we can do the stoichiometry. All right, so we've got 27 mils of our sulfuric acid that spilled. So what is the bare minimum sodium bicarbonate that we need in order to neutralize this acid. So if we're doing stoichiometry, what is the very first thing that we need to do? Balance the equation. All right. So take a look here before I write the balance. See if you can do it. Pause for a second. All right. So your balance, you should get a 2 here. Oh, I think I'm at the edge of what my program allows me to do. So there's a 2 in front of the sodium bicarbonate. And then we get a 2 in front of the water and 2 in front of the carbon dioxide. Every once in a while, I run into minor little issues with the surface area because what I'm doing, I have 3 screens set up here. I've got the main recording screen on my main monitor. I've got a view of what is actually being recorded up on another monitor, and then I have my iPad connected via Wi-Fi through a special program to my computer that tracks everything I write based on the screen. So took a while to figure out all the different pieces. But anyway, so occasionally I run into an issue with the program. But okay, so we have a balanced equation. Okay, so what we're looking at is we have a volume of sulfuric acid. We need a mass of sodium bicarbonate. So we're going from milliliters of sulfuric acid to grams of our sodium bicarbonate. Okay. Well, can we go directly from milliliters to grams like this of 2 different substances? No, of course we can't. Okay, so let's build a bigger roadmap. We're going to take milliliters of sulfuric acid. And what do we need? Because what were we given about the sulfuric acid? Well, we were given a molarity, right? And molarity is moles per liter, which means that we need to go from milliliters to liters. Okay, so we're going to go from milliliters to liters, and then liters to moles. And then once I have moles of sulfuric acid, I can do moles of my sodium bicarbonate, because again, when we do stoichiometry, we have to go through moles. And then I can go to grams. All right, I have a roadmap. So we had 27 mils. We have 1 liter in every 1,000 milliliters. Our molarity was 6.0 molar, so I get 6.0 moles of sulfuric acid for every 1 liter. Balanced equation, stoichiometry, I have 2 moles of sodium bicarbonate for every 1 mole sulfuric acid. I ran out of room, so I'll just add it down here. And then our molar mass, we have 84.01 grams of sodium bicarbonate for every 1 mole. Okay, looks good. Punch into your calculator. You should get 27.219. We have 2 sig figs, and you're going to get 27 grams. I think this problem is kind of hilarious because unless you're using 6 molar sulfuric acid, your grams of sodium bicarbonate are not going to be the same as your volume of acid. It just happens to work out with all the stoichiometry and stuff in this problem. So I think this one's kind of funny that you go from 27 mils to 27 grams. But anyway, there's our review on solution concentration. So hopefully this was a review. Maybe the way we did some of the problems, like going from a mass percent to molarity, you may not have done something quite like that in your prep chem class, but you should have encountered all of these different concentration terms prior to coming into this class. So hopefully this is a review. If not, practice some problems, because this is stuff that we do expect that you covered really in depth in your previous course, because it is such a crucial, like, basic thing that we do all the time in a lab setting.